Hey guys, welcome back to Gem City Rail. This is going to be active dust mitigation for model railroad, part 1. The motivation here was to come up with a relatively straightforward way to address airborne dust in the model railroad area of my unfinished basement. I have plans to address dust from the slab, as well as dust that falls from the joists overhead, but I needed something that could rapidly scrub the air if particle counts increased. I knew that I wanted to be able to automate fan speeds based on measured air quality, to run the fans faster when particle counts are high, and to run them more slowly when particle counts are low. The goal being to be as power efficient as possible while still controlling airborne dust. I found these inexpensive but surprisingly decent 400 CFM 6-inch inline duct fans on Amazon. And they do have a remote control module, and that's important for this project. Brand name is Too Lazy, by the way, which is a hilarious choice. In any case, I figured if they have a remote control module, I can figure out the control scheme and automate it, and that turned out to be true. Upon receiving the test unit, I found that it's a simple 2-conductor wire running to the controller. I opened up the controller and found it's just a simple potentiometer. I measured the pot at 10K and I scoped the signal coming from the fan unit. It's some sort of AC adjacent mid-voltage signal, but that turns out to be really irrelevant here. So in order to control fan speeds based on air particle counts, all we really need is a air quality sensor. I chose the Apollo Automation Air 1. I'm using Home Assistant for the automation itself, and then we just need some 10K pots that can be automated. So let's take a look inside the controller I built. So as you can see, it's a bit of a rat's nest in here. This is one of the hackiest builds I've done in a long time, but I wanted to get a prototype working quickly. I can always design a custom PCB at a later time, which who knows, might be years from now. So I decided to use the Seed ESP32C6 as the microcontroller. I have a lot of experience with these and they're simple and reliable. I purchased Born's dual gang motorized 10K potentiometers. Using dual gang pots is necessary because we need the MCU to be able to read the current position of the potentiometer. I'm using gang number 2 for the feedback to the MCU, while gang number 1 is what's controlling the fans. You'll notice that there are only 2 potentiometers installed. That's due to the fact that originally I was only going to build 2 air cleaners, one for positive bias into the model railroad area, and one for recirculation. However, once I started designing, I realized that the ESP32C6 has just enough pins to support controlling 3 fans and 2 indicators. The third potentiometer just hasn't arrived yet. Okay, so that's what's on the inside here. Now let's take a look at the form factor. For the prototype, I just decided to go with a surface mount design so I can get it installed and running quickly, but the final unit will be DIN rail mountable. As you can see, the enclosure is pretty deep. That's just to accommodate the motorized potentiometers. We have a USB-C connection on the side, which is what provides power to the unit. And then on top, we have 3.5 millimeter barrel connectors. And this is just what the fans use from the factory, and I didn't see any need to change it. Since the control scheme here is analog and just uses a pot, a nice side effect is that the controller doesn't require power to work. We can still manually control the fan. I am using a noise gate on my microphone, but hopefully you heard that. So let's go ahead and apply power to the controller. Upon powering up, the MCU will drive the potentiometers to their last known state, even before Wi-Fi and the ESPHome API connections are established. Once everything's connected, the red indicator will turn off and the white indicator will turn on solid, indicating we're in auto mode and that there are no faults or errors. Okay, and we can see the pots moving. So there we go. It's connected, and currently in auto mode and working. So let's go ahead and take a look at the Home Assistant dashboard. As you can see, the dashboard has PM 2.5 and PM 10 particle counts that are being read from the Apollo Air 1. We also have the configurable thresholds for fan speeds, both for PM 2.5 and PM 10. In the Home Assistant automation, whichever threshold is met first is what wins and what drives the fan speeds. I decided that 5 fan speeds were sufficient, which I represented as 0% or off, 25%, 50%, 75%, and 100%. Each of these fan speeds is able to be calibrated via the feedback voltage from the motorized potentiometer. So instead of a speed percentage, I currently have these levels calibrated for power draw. 25% is calibrated to 10 watts of power draw, 50% is 25 watts, 75% is 40 watts, and 100% is calibrated at full power, which is about 62 watts. The Home Assistant automation has 4 modes: auto, manual, full cleanup, and minimum. The automation is also able to be disabled entirely from the dashboard. Auto is what it sounds like. This is the mode that causes Home Assistant to track particle counts and set fan speeds in real time. Manual mode allows setting the fan speeds from the dashboard. So let's go ahead and try that. So if we put the system here in manual mode, you can see that our fan speeds are all set to 0 currently. But if you watch the potentiometers, if I set fan 1 speed to about 50%, we'll see the potentiometer move for that fan. Likewise, let's say I set fan 2 at 100%, and we will also see the potentiometer move for that fan. And of course, setting them back to 0 will take them back to their resting state. Full cleanup mode ramps all of the fans up to 100%. This can be useful as a preemptive measure if I'm going to be using my circular saw or otherwise creating dust. So if we hit that, we'll see the red light starts blinking, and that tells us we're going to full power essentially. And we see the motorized potentiometers moving to full power. You'll notice that only one potentiometer moves at a time. That's just out of an abundance of caution, so I don't pull too much power through the 5-volt rail on the MCU. Minimum mode sets whatever the currently configured minimums are for all 3 fans. Currently I have this set up for 25% for fan number 1, which is the positive bias fan, and then 0% for fan number 2 and fan number 3. This is just maintains that positive bias in the model railroad space so that dust wants to migrate outward at all times, but only drawing 10 watts. So now we're back in auto mode, and as a final demonstration, I'm going to introduce some aerosolized vapor here in the lab. The system should see this as a high demand particulate event and respond accordingly. Now it will take just a second for the sensor to respond here. There we go. And now the system is seeing a high particulate demand event, and it's setting all of the fans to 100%. And as you can see, our red light here continues blinking in a slow blink. That is what indicates to us that the system is currently in high demand mode. One thing to note is that I have configured the automation such that after a high demand event like the one we just simulated, the fans will continue at full speed for a configurable minimum duration. Since the fans create a lot of air movement, we don't want that air movement to fool the sensor into thinking the air is cleaner than it actually is, which could lead to system oscillation. By providing a minimum duration, currently set to 5 minutes, the fans will continue running at full speed for the minimum duration, regardless of where the particle counts sit. As you can see, our particle counts have largely recovered at this point, but the fans are still running at full speed. So that's pretty much what I wanted to cover here in the first video in this series. Subsequent videos will cover the filter plenum design as well as installation and operation of the system. And I'll say if you're a model railroader and you're not yet using Home Assistant, it's definitely worth looking into. it can automate a ton of infrastructure surrounding your railroad. I hope you found this video helpful or at least entertaining, and we'll see you on the next one. Thanks for watching.